Welcome to class, everyone. I am absolutely thrilled to have you here today. Consider this explainer your ultimate practical review sheet for understanding the physics of motion. If you've ever looked at the world around you and wondered exactly how to categorize the way things move, from, say, a falling apple to a spinning clock hand, well, you are in the exact right place. So take out your mental notebooks, because we're going to build a rock-solid framework for acing your physics exams. Let's get into it. Here's a quick look at our syllabus for today's explainer. We'll kick things off with defining motion and our key steps. Then we'll meet the translatory family. After that, we'll dive into rotatory and vibratory motions, followed by a review sheet to catch any common traps, and finally, we'll wrap up with a home lab and a little pop quiz.
All right, Section 1, Defining Motion and Key Steps.
So, at its very core, motion is defined pretty simply. It's when a body changes its position with respect to a reference point. Now, what's really interesting here and absolutely crucial to understand is this whole concept of a reference point. You see, motion and rest are entirely relative. You literally can't say something is moving unless you compare it to something else that's sitting still. That is the absolute foundation of physics. Once you establish that stationary reference point, well, then you can start tracking the movement. To make your lives super easy, I've broken this whole thing down into 3 golden steps to help you classify literally any movement you see. Step 1. Track the path. If it's moving along a line, it's likely translatory. Step 2, find the fixed axis. If the object is spinning around a central point, it's rotatory. And step 3, look for a back and forth movement. If it's repeating the exact same path over and over, that's vibratory. Keep these 3 steps right at the front of your mind today.
Moving right along to Section 2, the translatory family.
Okay, so the definition of translatory motion is a body moving along a straight line or a curved path without any rotation. The most important word in that entire sentence is without. Translatory motion means the body translates its every single point throughout its motion. Each and every particle of that body has to move perfectly parallel to each other. There can be absolutely zero spinning or rotating involved. None.
Now, the first sibling in this translatory family is rectilinear motion. And please, don't let the big physics jargon intimidate you here. Linear motion, which is just motion along a straight line, is simply known as rectilinear motion. Just think of the prefix recti as meaning straight, and you're good to go.
For example, think about the motion of falling objects. If you drop an apple right out of the tree, it drops straight down, right? Or think about the motion of a car driving down a perfectly straight highway, or an aeroplane mid-flight. Your main visual cue for this one is always to look for a straight, completely uninterrupted trajectory through space.
Then we have the second sibling, curvilinear motion. Honestly, the name itself practically gives you the answer. The word curvy obviously gives us the idea of a curved path. Hence, the translatory motion of a body along a curved path is called curvilinear motion.
Picture this in your head, the motion of a cricket ball flying through the air, or a football kicked way across a field. These objects move in a nice, clean arc, a curved path. But remember our golden rule for the translatory family? They do this without any rotation of their own axis. If they fly in that clean curve without actually spinning, boom, you have curvilinear motion.
And the final sibling in the translatory family is random motion. The source material defines this one perfectly, stating the irregular motion of a body in any direction without rotation is called random motion. The word random here literally tells us that something is moving without having any sort of proper, predictable direction at all.
To really visualize this, think about the invisible gas molecules in the room you're sitting in right now. They're moving in every possible direction. They have absolutely no proper direction of movement whatsoever. They just bounce off each other in this erratic, totally unpredictable way. That beautiful invisible chaos, that's random motion.
All right, Section 3, Rotatory and Vibratory Motions.
Next up on our list is rotatory motion. This happens when each and every point or particle of a body moves around a fixed point or a fixed axis. The easiest way to remember this is that when a body moves on the boundary or the circumference of a circle, it's performing rotatory motion. Your visual cue? You need to aggressively scan for that fixed center point. Just look around your daily life for examples of this. The motion of a wheel is rotatory motion. All the particles of that wheel rotate from that fixed central point. The motion of the hands on your wall clock, the motion of a ceiling fan, the grand motion of the Earth rotating, and even zooming way into the microscopic motion of an electron around a nucleus. For all of them, that fixed axis is the undeniable giveaway. Our third and final major category is vibratory motion. This is defined as the back and forth or to and fro motion of a body over the exact same path about its mean position. Let's actually slow down a second and focus on that term mean position. That just means the resting anchor. The object goes away from its rest position and then comes right back, repeating this over and over again.
Imagine the motion of the wires of a sitar or violin. Once you pluck that wire upward or downward from its rest or mean position, the wire moves rapidly up and down. It goes to and fro. As a result, it performs vibratory motion. Some other classic examples would be the swinging of a grandfather clock's pendulum, the motion of a weight attached to a bouncy spring, or even just a playground swing. They all have that mean, resting position they just keep passing through.
Which brings us to Section 4, our review sheet and common traps.
If we map these out side by side, it brilliantly illustrates how simple these differences really are. Think of it this way. Translatory motion follows a straight or curved path with absolutely no axis. Rotatory motion follows a circular boundary around a definite fixed axis. And vibratory motion? That just goes back and forth across a mean position. This right here is your master reference sheet. Definitely take a mental snapshot of it.
Now, listen up, because I need to warn you about the single biggest trap in high school physics. Students constantly confuse curvilinear motion with rotatory motion. And why wouldn't they? They both involve curves. But you have to look closely at your visual cues. Curvilinear moves along a curved path with absolutely no rotation. Think back to that thrown football. But rotatory moves on the boundary of a circle spinning around a fixed axis. Think of a spinning wheel. Please, don't let a curved line trick you into thinking something is rotating.
Finally, Section 5, your home lab and pop quiz.
I want you to turn your own house into a physics lab today. I challenge you to actively hunt for these motions. Look out the window and watch vehicles driving on the street. Recognize that rectilinear motion. Stare at your wall clock and mentally trace the fixed axis of its rotatory motion. Head to a park and identify the vibratory motion of the playground swings. Or simply drop a pen from your desk and watch rectilinear motion in real time. Physics isn't just trapped in textbooks, you guys. It's happening literally everywhere around you.
All right, time for a quick pop quiz to see who has really been paying attention. Here's the scenario. You pluck a violin string. It rapidly moves up and down from its resting place over the exact same path repeatedly. Think back to our 3 golden steps. What type of motion is this? I'll give you a second to lock in your answer. Think about it.
If you said vibratory motion, congratulations, you absolutely nailed it. The key clue there was that up and down movement from its rest-in or mean position. To sum up our explainer today, just realize how profound this whole topic is. Literally everything in existence is moving, from the vibratory motion of electrons inside the atoms of your own body, all the way to the grand rotatory motion of the Earth spinning in space. Everything in our universe is in a state of constant motion. Which leaves me with one final question for you to ponder until next time. What other unseen motions are happening right in front of your very eyes? Keep observing, keep learning, and I'll see you in our next explainer.